Okay, let's start. So, related rates. I forgot what section this is. I think it's 4.1. Related rates. Right, so one thing you need to remember about related rates is they're going to be word problems. Right? They're also an application of implicit differentiation. So the third test, test 3, that's going to include exponential growth and decay. It's also going to include related rates. It will also include optimization. All these 3 topics are word problems, so it's going to be very important that you're able to distinguish which one you're talking about. So how you would know here, it's basically going to be how the question is phrased. What you're going to notice is quantities will be described. And here's the important part, rates will be given. So they'll tell you about the rate of change of some quantity. Right? And then you will be asked to tell them about another rate. Hence the name of the topic, related rates. So it turns out if 2 quantities are related by some equation or relationship that we know about, I can differentiate that equation, and so their derivatives are also related by some equation. And so the rates are related whenever the quantities are related, and so we can talk about related rates. So if I know about the rate of change of one thing, and I know the relationship that ties that thing to something else, I can know about the rate of change of that other thing as well. And so that's basically the idea. So you're going to know that you're in this topic whenever I'm describing some quantities to you, and I give you the rate of change of some of the variables, and I ask you about a rate of change of one of the other variables. And so you know that's related rates. As opposed to, how do we know, just to jog your memories a little bit, how do we know whether we're doing an exponential growth or decay problem? What are some of the buzzwords?
Radioactive.
So if you see the word radioactive, odds are it's going to be an exponential decay problem. What else?
Half-life.
Half-life. What else?
Current amount. Current amount. Like find the current amount.
Not really. That's not necessarily just jumping at exponential growth and decay. What's the main thing that describes exponential growth and decay? What makes something grow or decay exponentially?
Increasing rate.
A little bit more specific than that, but you're kind of... Compounded continuously is another one, but the important thing that makes something grow or decay exponentially is that it's growing at a rate proportional to its current size. Right, so that's one of the buzzwords. So if you read something that says, oh, this is growing proportional to its current size, or this is radioactive, you know it's exponential growth and decay. If it's a word problem that gives you some rates and asks you about another rate, it's related rates. Now the good thing about related rates is it's going to be one of the heftier word problems you do, not as big as optimization, but it's pretty hefty. But the important thing is, I wrote all this down on the handout, so if you missed it, it's fine. The nice thing is, we have a standard sequence of steps to attack these problems, and you're pretty much always going to use this sequence of steps in this order, right? You might skip over a step depending on the question, and I'll talk a little bit more about that when we encounter it. But once you recognize it as a related rates problem, this is what you're going to do. You're going to go step 1, step 2, step 3, step 4. Once you get to step 6, you will be able to solve the problem. Okay? And so I'm kind of going to maybe describe the situation. So step 1 is obviously to read the problem carefully, because 1, you need to figure out that it's a related rates problem, as well as sort of get a general idea of the situation being described to you. Okay? Step 2 is to, given all that information that you've gotten from reading the problem, is to draw a diagram, right? A lot of times drawing a picture can help you get some ideas together. It gives you some ideas based on what the picture looks like. Okay, so you're going to draw a diagram, you're going to label it. You're going to label it very carefully. You're going to label things that are changing with variables, things that are constant with their constant values. The third step, somewhat optional, but it's highly recommended that you write down what you know and what you want to find. So write down what the given things are and write down what you want to end up with. Okay, that's because it's a word problem. I don't want you to get lost in the middle, forget what you're looking for. It's good to write those down and to kind of have those. It'll be easier to plug in. Step 4 is going to be to set up an equation that relates all the variables. Now, the diagram you drew will be very useful at this step, right? Because if it's like a rectangle, you can know, oh, I know that the area is length times width, and perimeter would be 2L plus 2W, things like that. It gives you ideas about the equations that you want to set up. But eventually you're going to have to set up an equation that describes the situation and that links all the variables in the situation, right? The 5th step is where the calculus comes in. You're going to differentiate implicitly with respect to time, okay? So what that's going to do is you're now going to get a new equation with a bunch of derivatives in it. Some of the derivatives you will be given because you're given some rates, right? So you can plug those in, and you want to solve for the rate that you don't know, and that's step 6, to actually plug in and solve for the unknown. Okay, that's basically the idea. It's always going to be how you're going to do it. There might be situations where you would skip over some of these steps, but in general, you kind of follow things in this order. So for example, if you're given an equation, there's no point in drawing a diagram because you don't need to use a diagram to figure out the equation if you're given the equation. So you just skip over step 2, but you literally just don't skip a beat, just follow everything else in succession. So step 2 and step 4 requires a little bit of ingenuity, but for the rest of it, for the most part, is just like following your nose. Once you have these things all set up, it should be straightforward if you remember how to differentiate. Let's hope we didn't forget that over the spring break. It should be straightforward to get to all the other things. Another thing you want to realize, based especially on step 2, is that there are some things I'm going to assume you remember, like the basic geometrical formulas for like rectangles and circles, right? I'd expect you to know how to find the area of a circle, or the area of a rectangle, or things like that, or the volume of a box, length times width times height. So there are some basic formulas that you should, just take a few minutes and flip through your high school geometry book and just remind yourself about those. Other than that, that's kind of really all we need to know to tackle these. So we're going to learn by doing, just going through a bunch of problems, and I'm going to show you how to apply all these 6 steps. I'm going to do the first 6 examples. The rest is for extra practice if you want to really know if you understand it in addition to the homework. So let's actually just jump into it. Okay. So we're looking at the related rates handout. Example 1. So it says here, a right circular cylinder undergoes expansion. So we have a cylinder that's expanding. Its radius is increasing at a rate of 1 meter per second, while its height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 meter and the height is 3 meters? So here, notice that we're given rates. Right? They told you how fast the radius is changing and the height is changing, and you're asked to find a rate. They ask you about the rate of change of the volume of the object, right? So that tells you that it's a related rates problem. And that tells you, do the 6 steps. Okay. So in reading the problem, that's one thing you would glean from it. This is a related rates problem. Okay, once you realize it's a related rates problem, you need to go through the 6 steps. Also by reading, so that's step 1, where we're reading the problem. The problem describes a situation to us that I'm going to use to help me with step 2 and step 3. So in step 2, probably not useful here other than just seeing the image, the familiar image would kind of spark your memory about the formulas involved here. But it's really a circular cylinder. The radius is one of the things we're given. The height is the other thing that we're given. Right, so that's kind of what we know from the picture. You might remember some formulas that go along with that picture. 3 is to write down what we know and what we want to find. What do we know so far? What are some things that we know?
The rates of the increase.
The rate. So how can I write that down? Rate of change of R.
dr, yes.
dr dt. So the important thing with related rates is that time is your independent variable. That's going to be important because you're going to need to know when you need to apply the chain. So we know that dr dt is 1. We also know, and I'm using dr dt because I label it as R. We also know that dh dt is 3, is 2. Okay, so those are given. These are meters per second, but in general I'm not going to care about the units. I mean, in physics class units are important, but here I don't care whether you write the units or not. Okay. One thing you should know here, and again, this comes from you reading the problem, is that both are positive because why are they positive numbers? Because we know it's increasing. So before we looked at this concept that when things are increasing, the derivative is positive, they're decreasing, the derivative is negative. Which means if they were to tell me, for example, that the radius is actually decreasing, I would need to put a negative sign here. Right? So you need to read very carefully to know not only the quantities and the situation, but what signs the quantities should have. Okay. What do we want? What do we want to find here?
Rate of the volume changing.
The rate of change of the volume. So how would I write that down?
dV over dt.
Okay. The rate of change of volume with respect to time. At what point do I want that? When what's going on?
R equals 1 and h equals 3.
When r equals 1 and h equals 3. So I read the problem, I recognize it as a related rates problem. That also helped me to draw this picture where my r and h are both variables. I'm using my r to represent the radius, my h to represent the height. In terms of these variables, I express what I know and what I don't know. So I know these, they're given. I made sure to put them as positive numbers because I know they're increasing. What I want is this guy in this situation. So that brings us to step 4. Now step 4 is to come up with an equation that relates all the variables. So what are the variables here? Well, r is a variable, h is a variable, and v is a variable. So can you come up with an equation that involves v, r, and h?
E equals pi r squared h.
That is the formula for the volume of a cylinder. Notice that, and this is kind of works for any prism. Notice that in a cylinder, it's basically the same shape that is spread throughout. It's called a uniform prism. And basically the area of such a thing is the area of the base times the height. So you get pi r squared h. And this is an equation that relates all the variables that I've used in steps 2 and 3. Okay. That's it. Now step 5, we're going to differentiate. Implicitly with respect to time. So this is my equation that I just set up in step 4. So now I'm going to differentiate that equation. Okay, so what is that going to be? What's the derivative of v?
dV over
dv dt equals
2r dr dt.
What about the pi?
Do we just leave the pi there?
Pi is a constant, so you can
Yeah.
just leave it there. So we have like 2 pi r h. Right, that's me differentiating the r squared is 2r. And then what?
Plus, is it product rule? Do we use product rule? Wait, do we use product rule here? Between r squared and h? Okay, yeah, plus, is it plus? 2, I don't know.
Something is missing.
Oh, dr dt.
dr dt.
Yeah.
Right? Now remember, this is the input variable, meaning if you're differentiating anything else, you need to apply the chain rule and multiply by its derivative. Right? So r and h are functions of time, you just don't know specifically what those functions are. So there's a function plugged into here that you need to figure out. Also, there are two functions, right? I have an r squared and an h, which means if I'm differentiating two functions being multiplied, I need the product rule. So I'm going to differentiate this one, leave that one alone, plus differentiate that one, leave that one alone. But because r, my variable is, my input is t, if I differentiate anything that's not a t, I need to multiply by the derivative. And so, hence I multiply by dr dt. Plus, now I leave the pi r squared alone, and what's the derivative of h? Start to t.
1, so it's dh over dt.
Right, 1 dh dt. And so that's the derivative. Which brings us to step 6. Now step 6 is plug in knowns. And solve for the required unknown. So in this equation, I'm going to start plugging people in. So what about dv dt?
We don't know.
I don't know. In fact, that's kind of what we want to figure out, right? So in step 3, we realize that's what we want to figure out. Okay, what do we know over here?
No, r, h, dr dt, and dh dt.
We know everything on that side. So it's pretty straightforward here. We're just going to plug these in. R was
1,
1, H is
3,
dr dt
1,
plus R is 1. What's dh dt?
2.
So this is going to be 6 pi plus 2 pi, so the answer is 8 pi. Technically it's 8 pi cubic meters per second, but I don't really care about the units as I said, so 8 pi would be an acceptable answer. And so that's your answer. This is how fast the volume is changing. Notice that it's positive, so the volume is increasing, which makes sense because the radius is increasing and the height is increasing. So we're getting a bigger cylinder overall, so we expect the volume to be increasing. That's how fast it's increasing at that point. So that's kind of it. We went through the 6th step for this problem. In principle, all related rates problems will be like this. The only possible hiccup, other than figuring out the equation, which this might be somewhat of a challenge, but once you practice enough problems, we sort of ask you about the same kinds of equations all the time. So coming up with the diagram and the equation is where most of the mental work comes in, but the rest of it is just following your nose and differentiating and plugging in. The only other hiccup is possibly getting to this point. There might be more than one unknowns, but don't freak out when that happens. All you have to do is like go back to step 4 and solve for any unknowns that you didn't know, and then you come back here and you plug them in. Depending on the situation, there might be other techniques, but in Calc 1, if there's something here that you need to know that you don't know, it's always back in step 4 you go to find it. Any questions on the process? Let's do another example. example 2. We're going to go through the same process. Step 1 is to read. So it's kind of a spoiler alert that this is a related rates problem, but you have to understand, by the time I'm testing you on this, it's not going to be obvious who's the related rates problem versus who isn't. You have to really read to figure it out. So notice here, again, we're given some rates. We're told about the rate of change of a rectangle, how its fast its length is changing versus its width, and we're asked to find how fast its area is changing. So we know it's a related rates problem, and we're given some information, which in 2, what's the appropriate diagram?
A rectangle.
This is just a rectangle, because he told us it's a rectangle. Alright, so I'm going to write a rectangle, I'm going to label it. What do you want to label it?
Length and width.
Okay, let's do L and W. Okay. They're both changing by what we're reading, so we label both with variables because they will change value over time. So it describes a rectangle, so my diagram is going to be a rectangle. What do we know and what do we want? Yeah?
We know dl dt equals 8.
We know the rate of change of the length is 8. It's positive 8 because we are told it's increasing. Okay? If they told us it was decreasing, I would have put a negative 8. What else do we know?
dw over dt was
We know how the width is changing, so this is going to be 3. And again, it's increasing, so that's a positive number. And what do we want? How fast is the area changing?
d80.
So let's call the area A. So we want dA dt when what's going on?
When the length is 1 centimeters and the width is 10 centimeters.
When L is 20 and W is 10. That's step 3. Step 4, come up with an equation that relates all the variables. So in step 4, we're going to do the equation. Our variables are L, W, and A. Can we come up with an equation that relates all of those?
A equals to wl.
Right. Area is equal to length times width. So 5. Now we're going to differentiate. How do I differentiate this with respect to
dA over dt.
what's wrong with this chunk?
dl dt w plus dw dt L.
So we apply the product rule here. So I differentiate the L, leave the W alone, plus differentiate the W, leave the L alone. Okay, which leads us to the very last step, which is step 6. Here we're going to plug in. So we know we want to find dA dt, so there's nothing to plug in there. Equals dL dt, we know that that's 8. Right? So that's another reason why it's nice to just write this down, so you don't have to reread the problem every time. You can just say, okay, dL dt, I wrote that down, that's 8. My W is 10, plus my dW dt is 3, and my L is 20. That's 80 plus 60, which is 140. And technically that's centimeters squared per second, but again, I don't particularly care about the units. If you write them, it's nice. If you write them, make sure it's correct, but it's okay to leave them. Questions on this? How's the topic so far? Is it okay? Is it?
Yeah.
That's good.
I mean, once you went through the hard work of figuring out what a derivative is and how to compute derivatives, everything else is kind of, just apply the derivative here. We did the hard work back in chapter 2. Right now we're just applying and enjoying the fruits of our labor. Let's look at example 3. A 15-foot ladder was resting against a vertical wall. Suddenly and without warning, the foot of the ladder begins to slide away from the wall at that rate, a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? So step 1 is to read. You realize that we were given a rate, specifically how fast the foot of the ladder is sliding away from the wall, and we're asked to find the rate. Step 2, I want to come up with a diagram. What's the diagram here?
A triangle.
It's a triangle. It's a right triangle specifically, because if I were to put the wall here, it's a vertical wall. There's a ladder leaning against that wall. So that's the ladder. And this is, of course, the ground. Right? So we kind of get this situation here where there's a right triangle being involved. Right? And now I can start to label the points on this triangle. Right? So what's the distance here, this length here?
X.
You can call it x, right? Just because I want to look like the xy plane. Right? Call that y. Notice I label these x and y because these guys are changing. The foot of the ladder is sliding away, which means my x value is moving. As that slides away, my y value is also moving. So these guys are variables. What's this guy? 15, right? That's important that you label the guys that are not changing with the values that they have. The length of this is 15. It will always be 15. That's the length of the ladder, right? If you label this by another variable, technically it's not going to be wrong, but there are issues that you might end up with. Because now you have 3 variables, you're going to find a derivative, there are going to be 3 variables around, and you might not recognize that z is a constant, so dz dt would be 0. And you might forget that, and then you're like, now you have this z and you don't know what to do with it, and you can't get rid of it, and you freak out. So it's just much easier to just call that 15, because it is a 15, and it will always be a 15. It's not changing, right? So you want to, when you do your diagram, you do want to label intelligently. Label things that are changing by variables, something that's not changing, label it with a constant, whatever its value is. But at the end of the day, that's our diagram. It is a right triangle, and that should hint to you the sorts of formulas that you'd want to use here. Move on to step 3. What do we know? What do we want to find?
You know, dx over dt is 2.
I know it's 2 because my x is increasing, right? As the ladder slides away, I know that my x is increasing. Right? So that's why it's a positive 2. Right? Based on how I drew that picture, it's increasing. And I think that's the only thing we get. What do we want?
What,
dy.
We want dy dt when?
When the foot of the ladder is 9 feet from the wall.
So here's where the foot of the ladder is. I want it when it's 9 feet from the wall, so that's them telling me the x value. So the information that you write down here, it will depend on the variable selection that you made before, so make sure you write this information down in terms of those variables.
Do you need to find what y is initially?
I don't know, we'll just keep moving. Keep moving to the next step, right? So you just go through the process. In step 4, what's going to happen?
Find an equation.
In step 4, we need an equation that relates all these variables. There are only 2 variables to worry about, x and y. What do you think?
X squared plus y squared equals 15 squared.
X squared plus y squared equals 15 squared by, it's called Pythagorean theorem. So that's our equation. Right, which the diagram kind of hinted to you that that's what you want to do. Let's move on to step 5. We're going to differentiate. Okay, derivative of x squared.
2x dx dt plus 2y dy dt 0.
Equal to 0, right, which is why we label it as 15. So we know the answer is 0, it's not something we have to worry about. Okay, now we want to plug in. And at this point we can take account of who do we actually know. I know the dx dt, that's 2. I know the x, right, that's 9. dy dt is who I want to find, so I'm not supposed to know that ahead of time. But what about the y?
Just plug it into that.
Right. So the thing here, when you're plugging in, you'd realize we need to find y.
Y.
Why? We need to find the variable y. And how you would do that is go back to step 4. So in step 4, we have an equation that relates all our variables. So if that's telling you what the variables are doing. So if I ever need to figure out what a variable is, go back to the original equation that tells me what it does. And so we'll go back to step 4. Right? You may or may not need this, but once you get to step 6, you'll realize what you need from what you don't. So you just run through the process anyway, but if there's anything you don't know, you go back to step 4. So we know that x squared plus y squared is equal to 15 squared. So when x equals 9, this means that I have 9 squared plus y squared is equal to 15 squared. And that means that our y is what? It's 12. Right? How do you do that? It's a 3, 4, 5 triangle. That's the shortcut. You could actually compute this. I mean, technically you could, but the idea is it's a 3, 4, 5 triangle. And I mentioned that here because it's a common little thing that would show up in a problem. They'll expect you to know like these little tricks. And so a lot of these problems will have that sort of built in. So it's we kind of know in a right triangle, if the hypotenuse is 5 and one side is 3, then the other side has to be 4, right? Or any way you arrange these numbers where the 5 is on the hypotenuse, these will have to be worked that way. So if this were a 3 and you didn't know what that was, that has to be a 4, and so on and so forth. And the nice thing about triangles like these are they work proportionally. So if I can multiply every one by the same number, and the relationship will remain the same, right? So these 3, 4, and 5 are called Pythagorean triples because they are numbers that work in Pythagoras' theorem. 3 squared plus 4 squared is actually equal to 5 squared. And so it turns out that if you multiply each of them by the same number, that relationship still will work. So in other words, if this side is 15 and I know the other side is 9, then this side has to be 12. So that's one way to actually look at it, because you'd realize that 15 is actually just 5 times 3, 9 is actually just 3 times 3, the other side has to be 4 times 3. But so yeah, we go there and we figure out that y is 5. You could also find 15 squared and then subtract 81, and take the square root, and ultimately get to the same place. But now we can continue with step 6. So what do we have here? Fit it all here. So our x is, I erased it, 9. What is dx dt?
Oh, dx dt is 2
Plus 2 times y, which I now know is 12,
times, we don't know what dy dt is.
times dy dt
Equals 0.
equals 0. Well, dy dt is what we want to find, so it's okay that it's the only unknown, but it should be the only unknown. I can divide both sides by 2, so I get 12 dy dt is equal to minus 2 times 9, and so my dy dt is equal to minus 2 times 9, 12, into this goes 6, 3 into that goes 2, 3. So my dy dt equals minus 3 over 2. And this is feet per second, but again, I don't really care about the units. And does that answer kind of make sense?
Yes. Because it's decreasing.
Because it's decreasing. So you realize that as x moves this way, the y is going to move this way. So y is decreasing. Right, so from the picture, another reason why you go through all these things is that you can kind of know what an answer would make sense, which means if you got a positive number here, you did something wrong. There's a computational error, or maybe your equation is kind of off or something, but you should sort of know what an appropriate answer would look like. It has the dy dt has to be negative here because my y would be decreasing. Any questions? Okay, we'll actually stop there. So the test is Tuesday, I guess. I'll send an email about it. I'm not asking any questions. I'm like, this isn't set in stone. I don't care.
Thank you.
Like if the world ends on the 9th, the test is the 10th. I don't care what your excuse is.
Even if we're all dead.
Even if we're all dead, I expect you guys to show up here. Sorry, Javon, I'm dead. I can't make the test. Oh, no. You're making this test. Okay. Stop there. I'll see you guys on Friday.